Hello friends, so in this video we are going to talk about steady flow energy equation, how it is implemented for compressor, condenser, expansion device and evaporator, and later on we are going to see the analysis of standard vapor compression cycle. So let's start. Vapor compression cycle has following assumptions. First assumption is the flow should be steady flow. That means any fluid characteristic does not change with respect to time at each of the component. So that is the first assumption. Second assumption is negligible kinetic and potential energy changes across each component. Across each component there is negligible change in potential energy as well as kinetic energy. So that's the second assumption. Third assumption is no heat transfer in connecting pipes. So all the connecting pipes are insulated, perfectly insulated. That is the third assumption. To analyze this vapor compression cycle, we are going to apply steady flow energy equation. That is nothing but first law of thermodynamics applicable to the open systems. So we are going to apply the steady flow energy equation to the four components. So four components of vapor compression cycle. First one is compressor, second one is condenser, third one is expansion device, and fourth one is evaporator. So we are going to apply steady flow energy equation to all these components. So first one is compressor. So this is the standard steady flow energy equation, and first we have to see the sign convention in steady flow energy equation. So for that, let us consider this is the system, and in this system if I am supplying the heat, that will be considered as positive. So heat provided to the system is considered as positive, while heat taken away from the system, that is considered as negative. Likewise, work provided to the system is considered as negative, and work getting from the system is considered as positive. So this is the sign convention that we are going to follow for the steady flow energy equation. So first we'll apply the steady flow energy equation to the compressor. So here you can see the compressor is there, and this is the condition of the refrigerant at section number 1. So at section number 1 some enthalpy will be there, some velocity is there, and some potential head is there, that is indicated by this H, V and Z respectively. Likewise at the section 2, enthalpy is H2, velocity is V2 and potential head is Z2. Now I will apply the steady flow energy equation. Before that, there are certain assumptions in the compressor. First is compressor is the device which is used to raise the pressure of the fluid, right? So there is no heat transfer involved in the compressor. So that is the first assumption. That means our compressor is perfectly insulated. So that's our first assumption. Second assumption is negligible change in kinetic and potential energy. Now if I apply these assumptions to the steady flow energy equation, then some of the term will cancel out. So since adiabatic condition is there, no heat transfer is there, that means this Q will not be there. Second, there is a negligible change in potential energy and kinetic energy, so that's why these terms will not be there. So ultimately the following terms will remain, that is m into h1 on left hand side, and right hand side m into h2. Now here it is written plus, but in case of compressor we are giving work to the system, okay, and we have seen work provided to the system is considered as negative, so here it should be negative. So ultimately we are getting like this, m into h1 on left hand side and right hand side m into h2 minus work provided to the compressor, that is WC. So work provided to the compressor, that we can find out by using this formula, mass flow rate of the refrigerant into H2, that is enthalpy at exit to the compressor minus H1. Now if you see this process on pH diagram and TS diagram, then this is your TS diagram, this is your pH diagram, and this process 1 to 2 is indicated by this red. So that's all for the compressor. Now condenser, if I apply steady flow energy equation for the condenser, then again there are certain assumptions. So this is your condenser, this is entry to the condenser, and this is the exit from the condenser. And condenser is a device where we are rejecting the heat. So QH amount of heat we have rejected from the condenser. So at the entry there is some enthalpy, there is some velocity, there is potential head. Likewise at the exit also, exit to the condenser also, there is some enthalpy, velocity and potential head. So let's apply this steady flow energy equation to the condenser. Certain assumptions are there in the condenser. No work done by the system. So condenser is used to reject the heat to the surrounding. So in case of condenser, we are not providing any work to the condenser, we are not getting any work from the condenser. So net work done for the system is zero. Again, negligible change in kinetic and potential energy. So if I apply these things to the steady flow energy equation, to the section 1 and 2, then again some terms will cancel out. So no work done is there from the system, and negligible change in kinetic and potential energy is there. So ultimately we are getting like mh2 on left hand side. Again, this should be minus because heat is rejected from the system, and heat rejected from the system is considered as negative as per the sign convention of steady flow energy equation. So this is minus into QH, that is equal to m into H3. So if I rearrange this, then heat rejected from the condenser is m into H2 minus H3. So if I see this diagram on TS and pH diagram, then it is indicated by this red color. Third device is expansion device. Again, this is the expansion device. So this is the entry to the expansion device, and this is the exit from the expansion device. So at the entry, enthalpy is H3, velocity is V3, potential head is Z. Similarly, at point number 4, H4, V4 and Z4. So assumptions in the expansion devices are: first one is it is adiabatic process, so no heat transfer occurs. Second, no work done by the expansion device, nor we are getting any work from the expansion device. Third, there is a negligible change in kinetic and potential energy. So if I apply this steady flow energy equation for the expansion, it will look like this. Then I will omit the terms as per our assumptions. Then the things remain on left hand side is m into H3, and on the right hand side it is m into H4. So that means H3 that is equal to H4. So if I see this diagram on TS diagram and pH plot, then it will look like this arrow color. Then the fourth component is evaporator. So this is our evaporator. So this is the entry to the evaporator, and this is exit from the evaporator. Evaporator is device where the heat is absorbed. So enthalpy at entry to the evaporator, let us consider it H4, velocity is V4 and potential head is Z4. Likewise, exit from the evaporator, enthalpy is H1, velocity is V1 and potential head is Z1. Assumptions in the evaporator is no work done by the system, and second is negligible change in kinetic and potential energy. If I apply steady flow energy equation to the evaporator, then it will look like this. Then as per the assumptions, I will cancel out the terms, so work done will not be there. Potential energy and kinetic energy is negligible. Then ultimately I am getting mH4 plus QL. See, here we are using the plus sign because heat is given to the system, and that is considered as positive. So mH4 plus QL, that is equal to m into H4. So if I rearrange this, I am getting QL that is equal to m into H1 minus H4. Remember, this is nothing but refrigerating effect. So if I see the same thing on pH and TS diagram, then this red arrow color indicates the process happens in the evaporator. Then we are interested to find out the COP of simple vapor compression cycle. So just now we have seen how we have calculated work input that happens in the process 1 to 2. Then how much heat is rejected from the condenser that happens in the process 2 to 3, that is indicated by this QH. Then process 3 to 4, that is isenthalpic process, H3 that is equal to H4, and process 4 to 1, how much heat is absorbed in the evaporator, that is indicated by QL. Then we are interested to find out the COP. So COP is nothing but refrigerating effect, that means how much heat is absorbed in the evaporator divided by work input. So how much work is given to the compressor. So the ratio of these two, that is nothing but COP of this refrigeration system. So I'm putting the values. So COP is equal to QL divided by WC. So I'm putting the value of heat absorbed in the evaporator and work required to the compressor. So if I reduce this mass will cancel out, and I'm getting COP as H1 minus H4 divided by H2 minus H1. See, from this process 3 to 4, we can see that H3 that is also equal to H4. So we can replace this H4 by H3. So COP is H1 minus H3 divided by H2 minus H1. We can write in this way also. So that's all from this video. Please like, share and comment to this video. Thank you.